These programs are distributed under a Creative Commons Attribution, Non-Commercial, No Derivatives license. You may copy and distribute these programs free of charge. You may not sell them, and you may not alter them. These programs are part of a study examining the value of podcasting as a medium for medical education. If this is the first time you are viewing a program in this optics series, send an email to jyoungmd@gmail.com with your name, position, institution, and city, state or province, and country. Thanks, and enjoy the podcasts. Today's discussion follows our previous lecture on prisms and is a practical clinical application of prisms called Prentice rule. We know that lenses are able to converge light to a point or cause light to diverge, and we'll be discussing those features of lenses when we talk about things like vergence later on in the course. Right now, we're going to look at what a lens does to a single ray of light. And we know that a single ray of light passing through a lens is bent by the lens, or can be bent by the lens. To the extent that the ray of light can be bent, we can view the lens as if it were a prism at a particular point and had a particular prismatic power, and in that sense is bending the light. Of course, the difference between a lens and a prism is that a prism does not vary in its prismatic power depending upon what part of the prism you strike, whereas a lens certainly does. Prentice rule is given as the number of prism diopters, or capital letter delta, is equal to h times d. D is the dioptric power of the lens, and I know this is not a unit that we've introduced formally yet, and we'll be talking about it later. Diopters refers to the strength of a lens and is a unit entirely distinct from prism diopters. So prism diopters is equal to h times the dioptric power of a lens. H is the distance in centimeters from the optical center or nodal point of our ideal thin lens. Now, in all of optics, and indeed in all of physics, you're going to have a much easier time if you're consistent with your use of units. And in all of optics, we are going to be using exclusively meters. The exception is when we talk in terms of prisms. And when we're discussing prisms, we're discussing them in centimeters. So we're still talking about prisms here. We're going to be using centimeters as our unit of distance. So h is equal to the distance from the center of the lens, the optical center of the lens, in centimeters. Okay, so let's do some problems here. A ray of light that passes through the optical center of the lens will emerge from the lens undeviated. So this ray of light is not bent. The distance between the ray of light and the optical center is 0 because we've given in this particular example that the ray of light is passing directly through the optical center of the lens. So h is equal to 0. I'm giving you as a given that this is a plus lens. It's a converging lens. It's a plus 5 diopter lens. So a Prentice rule gives us that delta, the number of prism diopters, is equal to h times d. H is 0. Therefore, the amount of prism diopters is 0. And this is consistent with our understanding of this ray of light passing through this lens because, as we see, it passes through the lens undeviated, unbent. Okay. In this example, the ray of light is passing through the lens 1 centimeter north, 1 centimeter above the optical center of the lens. And this is a converging lens. The rays of light are all bent to a point. In this case, we're examining one ray, but we see that it is bent downward. How much dioptric power is introduced by the lens, how much prism dioptric power is introduced by the lens at this point? Well, it's equal to h times d. D is equal to 5, so it's 5 prism diopters times 1 centimeter is equal to 5 prism diopters. Now, let's take a look at the cross-section of this lens here. We notice that, like other converging lenses, other plus lenses, this lens is thick in the center and thins out as we get towards the edge of the lens. imagine that we're going to orient two prisms. How would we orient them to mimic this shape of being thick in the center and being thin at the top end and bottom end? Well, what we could do is we could take two prisms and orient them base to base, so that the apices of the prisms are at the very top and very bottom of the lens, and the base of the prisms is at the center of the lens. And in that case, we would have a shape that, like the plus lens drawn here, is thicker in the center and thinner at the edges. If we pass through the top of that sort of stacked prism design, we would be passing through the prism that's oriented base down. And that is precisely what we're doing here in this example too. With this plus lens, since we're passing above the optical center of the lens, we're passing through a portion of the lens that gives us prism that's going to be base down. Again, if you look at the profile of the top half of this lens, it's thick at the bottom of its profile of the top half, and it's thin at the top, and that is what a prism is when it's oriented base down. So we know from our previous lecture that the ray of light is bent towards the base of the prism. Therefore, this ray of light is being bent down. And by how much is it being bent down? That's given by Prentice rule. 1 centimeter times 5 prism diopters. 1 centimeter times 5 diopters is equal to 5 prism diopters base down. In this example, the ray of light is passing through the lens 3 centimeters below the optical center of the lens. Prentice rule gives us that the total prism diopters induced in this diagram is equal to 3 centimeters times 5 diopters is equal to 15 prism diopters. And in this case, we are passing through a portion of the lens that is as if it were a prism oriented base up. And that means that the ray of light gets bent up. And by how much does it get bent up? We're given that by Prentice rule, 15 prism diopters. Okay, let's apply this in a clinical context. And the example that is typically given is this. Is you prescribe spectacles for a patient, and in this case the spectacles are -5 diopters in the right eye and -1 diopter in the left eye, and the patient comes in and he is intolerant to these spectacles. Now, in truth, a patient may be intolerant to these spectacles, but the reason that the patient is likely to be intolerant is not because of anisometropia, but because of anisoconia, a difference in the size of the images produced on his two retinas and a mismatch between that size. But let's take as a given that this patient is not anisoconic, and in fact has absolutely no problem, loves these glasses when he looks in primary gaze, when he looks straight ahead. But when the patient is reading, and this is not a presbyopic patient, this is a young patient, when the patient is reading and is looking down 1.5 centimeters from the optical center of the lenses, the patient complains of vertical diplopia and wants you to help. So let's calculate how much prism is induced by Prentice rule in this example. So the patient is looking 1.5 centimeters down. In the case of the right eye, the Prentice rule gives us that the prism diopters is equal to the dioptric power of the lens times h, which is the distance in centimeters from the optical center of the lens. 1.5 times 5 diopters is equal to 7.5 prism diopters. Now, this is a minus lens, and not shown in the slide here, but shown in your mind's eye, if you can picture this, is the profile of a minus lens. And what does that look like? The minus lens is thin in the center and is thick at its edges. We can approximate this shape by stacking two prisms oriented apex to apex, right, with their bases at the edges and the apex in the center, apices in the center, and that would also create a shape for us that would be thin in the center and thick at the edges. If we're passing through the bottom of this lens, as is the case in the example given, then we're passing through a prism that is oriented base down. So the total prism power induced in the right eye by looking 1.5 centimeters down from the optical center of the lens is equal to 7.5 prism diopters base down. Similarly, the amount of prismatic power that's induced in the left eye is equal to 1 times 1.5, or simply 1.5 prism diopters, again based down. The question then is, how much is the net prism induced by this arrangement? Is it 9 prism diopters or is it 6 prism diopters? Well, what we're interested in is the difference between the two eyes, since it's that difference that is going to induce diplopia. So the difference between 7.5 prism diopters based down OD and 1.5 prism diopters based down OS is equal to 6 prism diopters. Now, we need to not only describe the orientation of the prism that's induced, that's to say base up or base down, but we have to specify to which eye that prism applies. So we have two equally valid ways of describing the situation. One would be to say that the induced prism is equal to 6 prism diopters base down OD, or we could say, equivalently, that the total prism that's induced is 6 prism diopters base up OS, and they're equivalent descriptions of the same situation. Now, had the prism induced in the left eye been, let's say, 1.5 prism diopters base up, then the difference between the two would be additive in the sense that it would be a total of 9 prism diopters rather than 6. But that's not the case here. We will revisit anisometropic anisophoria in much greater detail later on when we include astigmatism, and we'll describe how we can solve these sorts of problems with spherocylinder lenses.